So today we will talk about construction sequence analysis. So first of all, why it is important? Because the main problem is that construction is not done in one go. It is done gradually and in stages, especially tall buildings and bridges. They have a very unique construction sequence. Like each building is made one floor at a time. They finish one floor. It's like a project. Then go to the next floor. Bridge also one span, second span, substructure, superstructure. So there's a sequence to that. So this takes 1 year to make, nearly. Over that time, the properties will change, the creep will come in, shrinkage will come in, many things will happen. And then if you just make the model for the building and they run, that means you're only analyzing the completed building, which is not the same as what happened during the construction. And those two are very different, we will see, especially for tall buildings. For small buildings, it doesn't matter much, but for tall building, it matters a lot. But even for small building, I will show you. So for the single stage assumption is that the full structure exists instantaneously. Thank you. So when we say run, we already have the full model ready, which is not what happens in reality. Then all loads are applied at once. That is also not true. Loads are applied in different times, like dead load, SDL, live load, earthquake, wind. They never come together as we assume at the same time. So when you think about it, that's very unrealistic way of doing things. Then no time dimension. This building was constructed in 1 year. Your analysis doesn't take into account that 1 year. So what happened? How did you miss all of that? Then one deflection state. We only look at one deflection state at the completed building. But actually, when the building is being constructed, it is going like this, being deflected this way, and people are making corrections at all the time. Making corrections all the time during construction. And this one structure grows floor by floor. And stiffness changes floor by floor. Stiffness is not the same. Today we have one stiffness, tomorrow we different stiffness because more members got added. Also, some members got removed. Formwork got removed. What about that? Because formwork adds temporary stiffness and then it's gone. And then forces are locked in at each stage. When you cast one floor, stresses because of that floor are already locked in. And that locked in stresses cannot be changed. You can add stresses, but you cannot change the stresses which were created by this floor. And this is something which is very fine point, but is a big difference because this cumulative stress and one-time application load are not the same. It's not because this is not a linear problem, it's a non-linear problem. So you can't add things at will. It has to be added in sequence because one sequence affects the other one. So all these things are very clear and very logical, but still engineers continue to ignore them and close their eyes and they think, oh, should be fine. Okay, so now let's look at that. There's a little bit light, but let's say in the construction single stage, you just get that single step building and you analyze it, right? But in construction sequence, we build one floor first. We apply all the loads to that floor. We calculate all the deflection and then lock those deflection and use this structure with the forces already in it and the deflections already in it to apply the next stage when you make the next floor. Then you add one more floor, step number 2. Then you add one more floor, then you add one more floor until you are complete with that. So the construction analysis happens 4 times. Analysis number 1, only one floor with loads on one floor, then 2 floors, 3 floors, and 4 floors. So that's the difference. Now you can easily see that the single stage analysis and multi-stage analysis are grossly different. So this is the normal analysis that will happen if you just apply all the loads together. And if you look at that center column deflection for this even small building like this one, I'm not talking about 40-story building. I'm talking about just small building. And the deflection here is minus 20.21 millimeter. If you do the construction sequence analysis, this deflection is 0.09 millimeter. Look at the difference. Even for a building as small as 4-story, you get like how many % difference? Now, why is that? Okay, think about the thing is that when you apply this load, when they construct this floor will settle, let's say 3 millimeter. It's 21 millimeter, right? So if I divide 0.021 millimeter, 1, 2, 3, 4. So let's say I divided by 4, this is about 0.5 millimeter, 0.05, whatever millimeter, it will settle, correct? But the site people, when they make the next floor, they will not make that floor shorter. They will level everything again because there is a leveling system. So the next floor will start from 0 again. No deflection, no relative deflection, and then so on and so forth. So every construction stage, the previous construction stage, differential displacements are corrected and building is leveled every time. So then you end up with much, I will show you later, just start to get the idea, okay? So the problem is that for construction sequence, the site people keep making adjustments called camber and level adjustment and alignment adjustment. And those adjustments keep changing the building's deformation from what you would have calculated earlier. So let's sink in. Now to talk about unsymmetric building. That was a symmetrical building, small unsymmetric building. Now walls on one side, this one, columns, and then shear walls. Okay. So normal analysis will tell you something like this, right? Now imagine, will the people making this building at this floor let it be like this, deflected? No, they will correct it, make it straight, so that this deflection cannot exist. Because at every floor level, any deflection by that floor, a little bit deflection, they already fix it and bring the building straight back. And then next stage, it tilt a little bit, and this floor, next floor, they bring it back. So every floor is being corrected as being built. So there is no deflection that is possible for this building to be like this. They will not let the construction people will not let this happen, because it's not building constructed in one day and load applied. It's being built every day. So any deflection happening until that point has already been corrected. So which means that now that corrected space, corrected direction has to go to the next stage, not the deformed stage. So that's what is happening. Construction sequence analysis gives you this shape, which is the correct one. See the difference, because people corrected the floor by floor deflection every time. So they will never let the building go out of plumb for gravity load ever. Do you understand my point now? That's why your gravity load deflection for this building is very wrong, giving you a wrong deformed shape. And if the deformed shape is wrong, bending moments are wrong, shear force is wrong, everything is wrong. None of the results make any sense, because deformation is the driving force behind everything. So you can see the difference, this one and this one. So this building is actually made like this. This is a typical form like this one, because they keep correcting and the building tries to keep shifting and they keep bringing it back. So you get this curve kind of thing. Because this tendency is coming from every additional load, but every time it tries to go this way, they keep pulling it back. Right? So the final shape will be very different from this is a very small building. It's not even 5-story. Imagine 40, 50, 100-story building. How many times it will be going like this? So the deformation for a gravity load for a construction sequence of a building will be like this. It's like a snake, because they're correcting every time of anything that is happening. But still the building has a tendency to go this way, so bring it back. Go this way, bring it back. So that is the essence of construction sequence and construction correction that needs to be included in the analysis. Everyone clear now? Good. So now you can see here, this one, and also lateral minus 0.8, minus 0.7. Look at the 8 times difference, 7 times difference. Not small for a building so short. Imagine tall building. So it's not right to miss the construction sequence analysis when you do this one. Make sure that you don't do that. Okay, now this is even more interesting than the normal building, the transfer system. Because now this is the normal analysis of a transfer system. If you just make this building like this, so what will happen is that the entire building will act like a big girder because every member is acting together, but that's not the way how it is constructed. The transfer girder will be made separately, and then other things will be added on top of that, not together opened, right? So if you do look at that, actually it will be like this, because the transfer girder is actually carrying the load, is not deforming together like you assume, because that was constructed first and with a different stiffness. So this will be so much different from the one that you assume. Once again, small building, tall building, even worse. So minus 2. This is the opposite one where the construction sequence will give you more deformation than less. Previous one, construction sequence give you less deformation than normal. Here, construction sequence will give you more deformation than normal. So you cannot estimate, or you cannot guess, or you cannot assume that my deflection, when my correction will be this way or this way. It all depends on the type of construction that you're doing. And then you can now see linear analysis, just a small building, 2 floors over a transfer girder. And then this one, you got to make first, then you make on that, then you make on that. Very different from that situation. And you can see here, once again, the moments and everything. 43, 89, almost double. So if you didn't do these construction sequence analysis, you will be estimating the main transfer girder's moment by half. That's a huge error, because that is the primary system carrying the load, and you made an error of 100% or 50% in the capacity. So these kind of things are extremely important when you deal with transfer girders and outriggers and belt trusses. They are all very different. They behave very differently from linear analysis and nonlinear construction sequence analysis. So transfer girder, construction sequence, and now this is another problem. The third one, the temporary structure, they alter everything, because how it is constructed will make all the difference. Whether you remove these props when the whole building is constructed, or you remove them after the first girder is constructed, totally different results. Because if you remove those props after the whole building is complete, then it's a single stage analysis. But if you remove the props as after you construct the girder, it's a construction sequence, different result. If you remove them after 2 stories, another result. So the sequence of propping and unpropping of a structure will change the results. And you need to understand how the contractor is going to make it for you to be able to construct your model the same way. Otherwise, the results will be could be very different. So we learned so many things very quickly. First of all, even for simple structures, construction sequence makes all the difference. Transfer girders are even more different. And sequence of shoring, unshoring is important in modeling these things. And not only modeling, but the actual response. And this is an old slide I dug up a long time ago. And you can see here that tall building and this tall building, how it shows the deformed shape just for gravity loads. So this will be how the building will act, because they will always try to make it correct, but the building will keep shifting. Below that, they cannot have a control, but every floor, they will bring it back. So the last floor is still aligned, but previous floors, they have no control. It went on. Some buildings in Dubai and other places, which are so highly unsymmetrical that they post-tension them later. So gradually, they keep post-tensioning the columns or walls or system to try to keep it bringing back. Okay. And the reaction also. So shear wall reaction, single straight is 16, and this one is different. Columns is 12, over is 11. This is for a small building. So you can see here that even the axial forces, the reactions, foundation reactions, everything is different from the 2 types of analysis. So the deflecting, deformed shape, axial forces, single And then other could be like this one, random, because depending upon how you make it and what is on the way, a transfer girder or outrigger will completely change this. And then slab level deflection. If this is the core wall and this is the column, the conventional analysis will show you that this wall is like this, because now comes the axial shortening of the column, because the column is more heavily stressed than wall, because wall is big, and we want to keep the stress and wall low, as we discussed the shear wall design, that you don't want to have high, but columns are fully loaded, heavily loaded. Stress value is very high. If the stress is very high, strain is very high. Strain is very high, shortening is very high. So you will indicate, the analysis will show you that theoretically the slab is like this, but they will not make it like this. They will make it flat. So that means they have to make the columns longer than they are. Every time the column is a bit longer, and then it shortens and becomes level. So that the correction, that is the level correction that the people at the site have to make. And that level correction has to go back to the analysis to be included. So this camber adjustments for all kind of things are very, very important in tall building construction. And they need to be calculated correctly. Single stage gets wrong, especially the outrigger forces, completely wrong. Once again, outriggers are cast after a certain time, and structure before outrigger is without outrigger, behaving differently. After outrigger, the force mechanism changes, but the forces locked in do not change. So that means that you have to accept that before outrigger level, it's a different structure. After outrigger level, now it will be a new structure with a new load path. The previous load path did not get changed. So those kind of things are very important for this thing to be done and understood. So, and the problem is this one, because this cracking or the floor leveling and the effect on the non-structural elements, the glass, the partitions, the panels, all of that will be critical, and they want to know exactly how much it will be so they can design their systems to accommodate that deflection. So obviously, if you go for linear, you will tell them, I need 20 millimeter level. They will say, oh, it's impossible. We cannot design a wall with 20 millimeter. But then you do the non-linear, and then you say, oh, no, I only need 4 millimeter. So those numbers have to be calculated. The actual as anticipated deflection and the distortion. So that's why this one, then especially MEP and vertical services, we don't think about it. Why sometimes waters leak in an old building? Why these things have damage? Why the water leakage problem comes? This issue of the differential settlement, differential axial shortening, creep and shrinkage, we will talk about that in a minute. So that's why the pipes which were originally vertical are no longer vertical. Pipes which are longer now have to be shorter. So they have to accommodate this shortening in the pipes also, not just structure. Pipes are installed later. So all these calculations are very important for MEP people. They want these numbers. How much do you need the tolerance for this and that and that? And normally structural engineers have to give them these numbers. And they have to design their system based on our deformation and our deformation. The facade people, everybody will need control on deformation. And if you give them elastic analysis, linear analysis, deformation, they'll be so wrong. So it's not just structural engineering problem, it's the entire building's envelope problem and MEP problem. So elevator rails, alignment, misalignment. Imagine that building that is going like this, right? I showed you. So the elevator rails have to accommodate that curvature of the building. They have to design for those. So all these numbers, they will ask you very precise numbers about the deformed shape of the structure at from 1 year now, 10 years now, and so on. So they can design their system. So you need to have a very detailed calculation. So conduit, pipe, junction boxes, rail misalignment at the fault, at the elevator, pipe stresses, leakage risk, all these things are related to buildings' deformations. immediate, during construction, and long term. So when is the stage construction analysis matter most? Building height more than 2-story, definitely transverse structures, any transverse structures, even one floor, composite columns, steel plus concrete, that mixed systems, columns plus walls, outrigger systems, podium and tower. These are all cases which are present in almost every building. So that means almost every tall building needs to do this. Okay, so first important thing now, so this is the overview. This is the important one that I want to discuss. The rest is mostly reading material because there's many slides. I'll just go over this quickly. I will stop over the ETABS modeling portion and sample building, but I will skip over. Otherwise, we need 3 lectures, which we don't need because most of it is just understanding. So I will just stop over some and skip over some. But column shortening, differential column shortening is one of the key features of tall building design, which is different from others, because this is really a challenge in the differential column shortening means that different columns in the same building shorten with a different rate and different amount, causing a problem on the floor level and on everything. Because if the floor level is not correct, bending moments, the beams will not be correct, and everything will be wrong. So that's why this axial shortening is the key. This is the difference between, so, and it comes from three components: elastic, creep, and shrinkage. These 3 things affect this number. And that's why the composite thing is important, because composites don't have creep shrinkage as much as concrete. So if some elements are composite and some not, you immediately create a problem between them, because the ones which are composite or steel don't have shrinkage and creep, but which are concrete have creep and shrinkage. So results on over time will be different. So axial compression of vertical members under gravity, all of that. So that is very simple. You can calculate the strain rate from this one, column shortening. And now elastic shortening, the 3 components. Elastic shortening is simple load divided by area, stress multiplied by modular plasticity, or divided by modular plasticity, strain multiplied by length, shortening. It's as simple as that. So that's elastic, very easy, simple. Creep shortening, this is the time dependent, develops over months to years, 10 years, creep continues. So even if you make the building perfectly level today during construction, the differential set shortening will start again with creep. And after 10 years, floor will no longer be level. Things will no longer be where you started, even you made all the corrections. So that means you have to calculate the time dependent and bring them back and make the correction in advance, that after 10 years, the building. So if you expect the floor to be level in 10 years, you have to make it unlevel at the site. And site people have to know that I need to make the column, this column 4 millimeter up, that column 5 millimeter down, that wall like this one, so that after 10 years, creep will be fine. Shrinkage, the same. Shrinkage is more short term, but still there. So these 3 things contribute together to complicate or aggravate the problem of column shortening. So now go back. Elastic shortening will depend on the stress level, which means if the column is larger, sometimes the architect wants the column larger. So if you make a column larger than required, that means your stress, elastic stress will be different. The first component will be different. Then you have 2 columns, one is steel, one is concrete. Creep and shrinkage now is different. If you have composite, again, you have a complete and creep and shrinkage different. Shear walls are another category altogether, because they are the biggest components there, but they have very low stress, very low first component. Also, second component may be large or less, depending upon how we cover them and the temperature variation, and then whether it's air conditioned building or not an air conditioning building, whether it's the outer column or interior column. Weather conditions are different, temperature is different, humidity is different. So all these factors add up to make this thing even more complicated. So that's the elastic shortening. Then we have creep, time-dependent shortening. You know about that. I don't need to spend time. So creep will be a problem. And then shrinkage will also be a problem. Both creep and shrinkage are independent of the load levels. They just depend on the size, the type of concrete, the climate, the water cement ratio, all of that stuff. So, but they have to be included in the analysis. That's the key, long-term analysis. So it's not just construction sequence in the way things are made, but after they're complete, what happens to them in 10 years, 5 years, 20 years? That's it, long-term analysis, another step in construction sequence. Under construction and post-construction. So because of that, you can see here that the settlement in different columns will be 22 millimeter, 8 millimeter, 12 millimeter. Look at the cover, and wall is only, let's say, 16 millimeter. So every column will have a different level. This is not acceptable because that means the floor is not flat, right? People expect the flat floor, and which means that the floor which is flat today is not flat tomorrow. So how do you handle that problem? You have to make the floor unflat today, so it will be flat tomorrow. But then the unflat floor exists today, which is also not good. So somewhere a compromise has to be made with these acceptable limits. That okay, total acceptable limit of the floor is 3 millimeter. Okay, I will make it 5 millimeter up, so it will go down by 3 millimeter, something like that. So you play around with the tolerances and play around with the calculations to get something that will be more or less acceptable during the life of the structure, at least 10 years. Okay, so this kind of diagrams, you need to make a diagram of this kind to give to the site for their error correction for their site. That what is the level correction they should make? They should not make it flat. Their tendency will be, if you don't give them this information, they will just make it flat because that's what the default construction is. But you have to tell them, no. Don't make it flat. Make this column 5 millimeter above, this column 3 millimeter below, and so on. So that after some time, it will be flat. So interior columns normally shorten more than the exterior columns because they have more load. Exterior columns have less load. Sometimes the size is the same, and walls shorten much less. So in general, every column has a different axial shortening history as well as the starting number. Of course, we know why columns shorten more than walls because the stress level is high. Walls are supposed to be designed for bending. So we keep the stress levels low for axial load. Columns are designed for axial load, so they can be high. So there is a clear difference. At least stress can be as different as 2 times between wall. So strain will be different 2 times. Then concrete strength is different. That makes the E different. E is different, rate is different. So if you change the concrete strength, that also changes because elastic shortening depends on E. And FC also changes creep. FC also changes shrinkage. So changing the concrete strength affects all these things. So you can see from here that slab level building, it will be different. So what you expect and what actually will be that you will not get the same thing. This is theoretical. This is after long term, creep and shrinkage. Because theoretical or single stage analysis will not give you that problem. But here, this can be the problem if you include long-term effect. So then it will affect the slope, tile cracking, facade seal risk, leakage, door window distortion. Doors are not closing. Some door is always opening. Some door is always closed because of this kind of thing, right? They're jamming up because things are moving up and down. So these small things that people notice in their building are actually originating from these long-term effects. So this is the construction stage analysis with proper correction, with proper analysis, you can achieve a in-service level which is straight, which means, first of all, do the construction stage analysis, do the long-term analysis, apply the correct values on the site for the cambers and adjustments so that in service level, things will be okay. So I'm going fast because you can just read this one. So real construction versus single stage construction. So just this comparison. I've already talked about most of this one. This is more like how to do this one. So load sequence at each stage is very important. Let's stop here a little bit. What loads are important? In fact, self-weight is probably the most important because this is what the construction is going to be, and you have no control on that. Construction live load which is happening during construction, is also important. And sometimes for bridges especially, and sometimes building, the construction load is also included in the construction sequence analysis, because sometimes it could be very high, very heavy. And sometimes the shoring, unshoring. So all of the live load which during construction also has to be modeled or can be modeled. Then superimposed dead load. This is very important. Their timing is very important. When are you going to place the floor tiles? When are you going to add the partition walls? When are you going to place the furniture? Now and 1 year from now, different results. So then you have to know how this is going to be, or you can specify. Don't do this, do like this to minimize this. So either way, the superimposed dead load is where the control is with the engineers. They can control it or they can accommodate that. Then live load, final live load, which is occupancy last applied. Live load normally does not affect the construction sequence so much because it's come and go, but still it could be very heavy if it is storage, like library, books. Books are like dead load, but we normally consider them live load. So if it's a library, for example, those books are going to change everything. Storage facilities, other things. So if there's a storage facility, once again, it's a live load, but it's almost always there. So we have to see what kind of live load are we talking about and where to include that. So flows locked in at each, as I told you, the stresses are locked in at each level. And those locked in stresses cannot be changed by another construction. And they are not the same. So 1 + 1 is not 2 anymore, because of the way 1 is added to 2. The sequence is important. The timing is important. So once again, you can see here that this one here, it will shift. The axial shortening or the loading will shift from core to columns, from columns to core, and then cores to column. Deflection will go this way, forces will go this way. So wall will start to carry more loads later when the columns go down, and they will transfer to the wall. But the deflection will shift from this to that side. So both things are opposite. So it's like a cycle. In reality, when we have a differential settlement like this one, we have a redistribution of loads. And because of the redistribution of loads, stresses tend to get slightly even out. So the cycle continues. So when columns come down, they transfer the force to the core wall. Core wall has more stress. It also goes down a little bit, slightly. But then this cycle continues. But normally cores are much larger. So their small shift of the load doesn't change the distribution much. So slab tilting, rotation, all of that you can see. Okay. Now let's look at the nonlinear nature of the stage construction. Why is it nonlinear? Because like I mentioned to you, it's not summation. It's not automatic summation, because each result is based on a different stiffness and different time. That's why they can't be added. So the results depend on the order of the sequence, and we have seen that already. P delta effect. So this is the first load path dependent problem. The results depend on the order in which they are applied. Secondly, the P delta effects, lateral moment from gravity loads on displaced structure. I will show you all these things later, because like you have seen that building, right? The building is, if going like this and going like this, P delta will be very different. So P delta is applied on the final stage of the actual deformed shape, not on the assumed deformed shape. So that also changes the P delta analysis. So is it absolutely essential that construction sequence analysis is combined with P delta analysis? Because P delta changes the results a lot, and it will come back and change the deformations again. So that cycle is very critical. So when you run construction sequence analysis, P delta has to be included. So it becomes nonlinear. Then material nonlinearity, time-dependent concrete. I told you, so there are 3 things in time-dependent concrete. First of all, it's a creep problem. Second is age of concrete. As the concrete becomes older, the strength increases or decreases? Increases. So that age factor also needs to be accommodated into the analysis. Then shrinkage, of course. So we have to separate the elastic, creep, and shrinkage into the analysis. That's why when you do the analysis, you will see that the construction sequence analysis, you can specify the order of construction for elastic, you can specify the time and the other properties for creep and the shrinkage. So 3 components are added together systematically. First, order of construction, then time starts after that, and then changes due to the change in the properties. First, geometry change, loading change, then property change, in that order. Floor by floor stage construction analysis, there's an example that we will see here. So just forget about that for now. Okay, so let's go to the ETABS. Before I go to ETABS, let me discuss a few more things which are relevant to the construction sequence. The first one is transfer girder and transfer slab. I already showed you the problem, why this is so critical, because transfer girders, depending upon when you make them and when you remove the false the supports, is going to change the results completely. So that's why any building which has transfer girders or slabs, construction sequence must be checked with the contractor how they plan to construct it. Or you need to specify that this transfer girder should be supported for 12, 1 year or 1 month or until fourth floor, whatever. So the construction on site and your assumption in analysis must match. That is very important. So normally construction methodology is written by the structural engineer with the documents for contractor to follow, or the contractor submits the construction methodology to the designer to accommodate in the design. Either way, it has to be matched. So many stories in the field where things did not match. The most common one is a bridge, someplace where they were supposed to construct a bridge from both directions and meet in the middle, but the funds were not enough. So contractor decided to make one side first and move this formwork to the other side. By the time he starts this one, creep already made it. When they bring it here, the 2 sides of the bridge are like this. And they have it because they didn't, make this correction. So things like that are common. Building is sold, people come back later, find it very different from what the drawings were, and so on. So that's why the transfer structures are unique in stage construction. As I mentioned to you, all of this one. So you have to have before transfer is cast, transfer cast floors above the loading, and certain construction configuration. So very important, like I said, whether the transfer girder will be cast together with the rest of the structure, will be cast first, form removed, then rest of the, because then it will support construction load, it will support the temporary load, it will support everything. And you have to design for that, which is, common. So that's why knowing the construction sequence for a transfer girder system and also for outriggers and belt trusses is very critical. And like I said, it can go from compression to tension in some cases. Some column which is actually sitting on the transfer girder, and it's supposed to be in compression, transferring the load, may actually be pulling the transfer girder up if you do the wrong way, because upper structure will become stiffened and start to act like an arch and start to pull the transfer girder up or hold the transfer girder up. So it can happen easily. As you build the structure, some portion of the structure starts to act like a wide arch and start to be so stiff that it starts to carry the structure below that. So all these things are known phenomena. So another one, transfer girder slab or girder cannot span unsupported when wet concrete is poured, obviously. So which means that the casting of the floor of the transfer girder and the removal of the formwork and the next stages have to be completely coordinated between analysis and construction. The effect of shore removal, I already mentioned this one. Shore carries all the transfer slab self-weight. So before shore is removed, this is very important, because when we have the shoring, I showed you that diagram, then it is carrying all the load. The structure is unloaded completely. So it has no forces. Even if it is hardened, it has no forces in it. So if you construct anything on top of that, it will not affect the load will just transfer to the shoring. Now, depending on the shoring removal, the load will then transfer from one to the other. So that's why sub-transfer columns, light or zero load, transfer elements, low stress. After shore removals, sub-transfer columns, sudden large load will come to them, and then transfer element, full design moment will be activated in that one. So that's why studying this in different scenarios should be done. You should study what happens if they remove the shore before time, after time, which one is better. Then you run a few scenarios, and then you say, okay, this is the best one. I will recommend this for construction, most economical one, almost, with the least stress path. Then long-term deflection can be 2 to 3 times. We already know that. So, like I said, tension in the sub-transfer columns, there can be in tension, wrong transfer element forces, wrong long-term deflection. All this can be, and these are marked in red because it's really serious. So transfer girder, any tall building with transfer system, you must be very careful in analyzing and designing those components. Podium and tower system, another special case. I just want to go over and emphasize what are the problems. So podium and transfer has another story because the foundations now, which we will study next, now loading is going to be different at different times during construction. When the podium, let's say the podium is 6th floor. At 6th floor, podium and tower are the same. And now the tower is going up, podium is not going up, but the foundation are normally connected. So now the pressure levels on the tower will be increased substantially. So now they will start to settle more than this one. So now the floors which were originally level, no longer level, this now going down. So that means suddenly this floor, which was the same, that when you constructed, now this tower portion start to go down because of the soil is now settling. And then what you either break it or you make it tilt. You have an expansion joint. Expansion joints have another problem because the floor is not level. So you have to make all these calculation corrections beforehand to actually make the tower longer, higher than the podium, so that when they settle, then they are at the same level. So these kind of things now become construction sequence plus soil structure interaction together. So that's why I put this topic, construction sequence and soil structure interaction, as one. We will talk about the soil structure later, soil structure interaction. But this is where it will become important. So low rise, wide podium, typically 3 to 8 floors, splendid tower rising from the podium 20 to 60 floors. So suddenly on the same area, this is 6th floor, and I step on this side, this is 60 floors. This is a common line. For me, I don't see anything because I'm walking on the shopping mall, right? Shopping mall, this side is just only 4 floors. That side is under the tower. We can't see the difference. But imagine what is happening at this interface. From the long-term effects, from the axial shortening, from the soil structure interaction, from soil pressure, so much is happening in the two regions. So we need to manage this problem well. So podium fully built, construction scenario A, podium completed first. So podium fully pissed, tower core, after that the tower rises, then tower floors are added and all loads in service. That's one way to do that. Sometimes they will construct the tower first, podium later, so that the tower has already settled wherever it is supposed to be. Then you just make the podium on level with that. That's another approach people can follow, right? But then you need a construction either gap or construction joint between that. Construction B, tower core races ahead, and this podium follows later. Like I said, we make it later, right? So make the tower first. So once again, depending upon what the scenario is, the results will be different. And construction sequence analysis needs to accommodate this in analysis. So different stiffness, podium versus tower, wide, higher, high in plan stiffness, short, small axial shortening, many columns, load is well distributed, low stress per column, obvious things, but you need to know. Slender, low lateral stiffness, tall, large cumulative shortening, fewer columns, high stress, more creep, right? So you can see here, two parts of the building having very different demands, structural properties, but they are connected together. Because people don't like expansion joints. Remember, now these days, expansion joints are a no-no in construction because they leak, they create problem, they're a maintenance hazard, they break the floor. So most of the people and clients do not want construction joints in the buildings anymore. So what you need is you need kind of a leveling slabs in between, which can move up and down. So you allow, rather than expansion joint, here you just extend it to maybe 4-meter long soft slab around that, which can accommodate the movement without cracking. And still the building is connected. So there are many ways to do that. So this is a problem. I keep getting this question. How do we create and you will have the same problem because many of you asked me, should we include the podium or not in your model? Because including the podium, not including the podium is a huge decision. And especially now with many buildings having multiple towers on the same podium, it's quite common. Bangkok 1, have anyone seen that? There are 6 towers in that one complex with a common parking underneath. That means there is one podium supporting 7 towers sitting on that, 6 towers sitting on that. Imagine the complications of the construction. They were all constructed differently. Height is different, loading is different, but they're all, and you people who walk around don't have any idea what's going on with this complex system. How do you even model that building with 6 towers and one podium? Do you create one ETABS model? Do you create 6 ETABS models? How do you connect them together? How do you make sure that they are compatible? How do you transfer forces from one to the other? It's unimaginable problem. So my point is, we are just now taking it for granted that we can, because now ETABS has what is called multi-tower modeling approach. The problem is, just 5 years, 10 years ago, ETABS did not have this idea of the multi-tower approach. So if you create one floor, it will consider that to be one diaphragm. No matter how many towers are there, they are assumed to be all connected by an invisible diaphragm. This is only recently that they created this, where you can create each tower with its own diaphragm and separate them from each other. Otherwise, you get one mode shapes, you get one everything. So even if you were able to model 5 towers, ETABS internally will consider them to be one big building, invisibly connected by a diaphragm. So the problem is that model that huge is very, very difficult to really do any detailed work because it's just too big to understand and too big for any single engineer even to model. So you have to think about, see, every time you have this question, think about me. What would I do 40 years ago or 30 years ago when I had none of these tools? Engineering is about that. Engineering is not about ETABS can model it 6 towers. I will model 6 towers because ETABS can do it. That's not an answer. And that's not the way that we should be thinking at all. We must think as like engineers. What is the problem that I'm trying to solve? What are the issues? What is the thing that I should remember? That's the way to think about the problem, right? Because if you don't, then you will not understand whether ETABS did it correctly or not. So the right way, the thinking way is, like you said, take each tower, model them above the podium, for example, assuming that the podium level, they are on a big foundation, so they are kind of fixed at the podium level. So take each tower separately and finish it, stop it at the top of the podium. And then do all the analysis for lateral, this and that, whatever you want to do. And then you can get those forces, right? And then create a model of the podium and then apply those as forces on this one that you obtain from each tower, because you take the foundation to be that podium. So you just transfer those forces from each one of them. Plus, you can transfer the deformations also, because we can do that. And then you run the podium analysis for those forces. And then you can run different scenarios, only one tower constructed, two tower constructed, three tower constructed. You just have a different load cases for each tower being constructed. Then you can understand what's happening to the podium. So once you have clear understanding, then you can go ahead and create a full model also to just for fun, and you can see some results. But it will not give you understanding. But if you just rush and create that model, you will just spend 1 year creating a model that you are not sure if it's correct or not. So always do a simplified stick. Some people will just do a stick thing. They will consider each tall building one cantilever, because that's what it is, right? And then get the overall forces, get all the stuff first done, total forces, and then just apply. If I was doing that at that time, I will just draw and I will just put those point loads and bending moment forces on this system and check the system first, then gradually add more and more and more and more. Right? So please remember to simplify the problem, understand the mechanism, and then rush to ETABS modeling 6 towers together. Okay. Anyway, so coming back to this one. So this one, that's why I'm saying that there are many ways to do this thing, and you should be able to simplify. Get to a WL square by 8, PL by 2 kind of a solution that you can verify by yourself. Then you do the stage interconnection, check interface forces. All that can be done step by step. We remember one building in Philippines we did that has 3 towers and a podium. And the construction was another one after 5 years, after 3 years. And we have seismic analysis. You have all these kind of forces in the podium design, a lot of things. And we did the same thing because each tower has to be constructed. So podium is done, only one tower is existing for 2 years. Then another tower will come. Then another tower will come. During that, earthquake will keep coming, right? So you have to be able to handle all those scenarios. Okay, ETABS implementation, last step. So this is the building sample model, and we are doing the model. So first of all, construction stage analysis has 2 items in ETABS, 2 ways to do that. Your way and my way. Your way is go there, auto construction sequence, press the button, go have coffee and see the results. So ETABS will automatically create construction sequence for each floor, whatever, run it, and you get the result. But you have no idea what ETABS did and what you are supposed to do. But they have put that option for a quick one. Don't do that in real structures. Real structures, you have to understand exactly how the building is constructed, because it's not the way ETABS thinks it is constructed, right? So which means that you have to understand. So to create a construction sequence, you have 4 or 5 tools in your hand. This, remember the basics. Everything else is detailed. Number 1, you can add a structural group. You can create a group of your structure elements, beams, columns, walls, whatever, any group. And then you can say, this is my group number 1. And then you can say, construction sequence, step number 1, add group 1. So that is called add structure. Then step number 2, add load, applied load. Then you can say applied load to that group, this load case. So you have a load case, load pattern. Then you say this group, apply this load now. So you can build the geometry and you can apply the load independently of each other. Then you say now, step 2, make this group, add this group to this structure, apply that load to now this structure. So program will analyze the first group, get the results, lock them in, construct the second group, apply the next forces to the whole structure, lock that in. So you just keep on adding construction stage. Each construction stage has the option of adding a structure, applying a load, changing section properties, where you can do the nonlinear, the things, and then also remove structure. You can also say that at this stage, remove these columns now. So you can model the temporary columns in the structure, formwork removal. So in one stage, you add those columns, Then after that stage is complete, or 3 stages are complete, you come back and remove that group. So it's very simple. Logic is very simple. Structural elements have groups. Each group can be added or removed. Load can be applied or removed. Section properties can be changed during a stage. That's it. Everything else is then, and you just follow that, and then you run it. And then you should get the, and then each step results you can see separately. That's the difference. So program will run the analysis if you have 20 stages 20 times. So you have 20 results, 20 stages of bending moment, 20 stages of deflections, 20 stages of everything. And when you see, you can select which stage. When you do the design, then you can add any stage or final stage, because each one is a separate case now. So when ETABS does automatic, it just assumes, and then you say, okay, consider 3 floors at a time, or you can specify 5 floors at a time. So it will create group 5 floors, stage 1, add group, add load, go to next, add. That's a very simple way of doing things, right? You don't have to consider every floor as one stage because it's unnecessary. 3, 4 floors together is fine for preliminary estimation. So that's just about the process. It's not complicated. Then comes the long-term analysis, which is a separate one, that you do a long-term with age assigned to the groups, right? This one, construction start from here to here, creep, this one, this. So those 2 things are there. That's the summary, short summary. So that's how you add it. And then a discrete step, 1 stage, 1 floor or group of floors, an action within a storage, add elements, remove elements, apply load, change stiffness, right? So this is what you can do by yourself. The gravity load applied within the stage, self-weight, construction live load, all of that. So complete control on how you do it. So that is those are the forms. So P delta plus large displacement, all of that you can select. You must always select P delta for construction stage. Large displacement, the difference between large displacement and normal displacement is that large displacement considers the change of the geometry during the analysis. Let's say, like I showed you earlier, if it's an arch and deflection becomes a cable, it will consider that. If you don't do large displacement, it will remain an arch. Then, so for example, step number 1, second step. So for example, it's 2 floors, then 1 step, and then, so if this 1 floor each, you get like this one. If 2 floors each, you get that one. So sometimes you can say, okay, just make 2 floors, 3 floors at a time, because it doesn't matter so much. So you can do that. Or you can do each floor, because it takes more time to run it, more data to analyze. So defining load, like I said, dead load, superimposed load, construction live load, all can be specified here. And then here, all the load cases are here, the details are here. So please read that and try that when you do that. Follow this sequence. And look at this one, tree view. The tree view shows you every stage and what is happening in each stage. Quite, comprehensive and list of what is happening to the structure while it is being analyzed. So you can go deep and study everything. Then specify long-term, the time-dependent. When you specify time-dependent, so enabling time-dependent material properties is a separate option, like I said. So you can enable them for a particular construction stage and give that time. Because this construction stage is going to be 5 years long, 10 years long. So you specify time-dependent on that, and then it will go to the next one. So you can specify what kind of creep model you want, what kind of shrinkage model you want, and so on. And then you can see the age at loading. Okay, this is the age at loading. 1 year, 2 years, 10 years. So that you can see the graph with that one. So age, when is certain load applied over time, not over sequence, also over time, right? So all of that can be included in this analysis. So running the key settings, analyze, set the load case to run, set nonlinear parameters, P delta is on, maximum iteration may be 50, conversions like this one, default number, set output and display option, save results for all stages, not just final stage. This is very important. Otherwise, no point. You must save every stage results separately so you can go back and look at them, right? And then run analysis, 2 to 20, actually one, depending on your machine that you have, could be much longer. And then check analysis log, confirm all stages converged. Because in nonlinear analysis, some stages may not converge because you specify the wrong system over there. So spend some time checking everything. So cumulative versus incremental, so total deformation versus incremental at each location. The important thing is to not just see the total, see the change from one stage to the other. Then you will really understand what happened during that stage. Otherwise, you lose the understanding of the construction sequence. Okay, this is a 20-story building, just some idea how that is done. These are the results, comparison between single stage and multi-stage. So you will see, I showed you already, the results are different. Base results are different. Axial forces comparison, auxiliary forces are different. So you can compare with each other. The single stage, that results here, 284 and 116 and 173 and 99. See the difference change? So big numbers will change at the bending moment. So this beam here, bending moment here is 284. This is only 173 because the deflection is different. It's much less. So the moment will be much less. So these kind of things you need to understand. You must look at the connecting floor elements. They will be affected a lot. So same is the case with deflections here and here. 21 millimeter versus 1.5 millimeter. That much different between the two because of the correction along the way. Same is the case here. 21 versus 1.5. 17 versus, so look at that. Single stage construction shows 11 millimeter and 17 millimeter. This one only shows 0.88 to 0.16. Relative displacement with that one. So much different between the two these stages. And then forces different. Okay, these are all the results that you get from that. So common mistakes and troubleshooting. So creep not enabled. Sometimes we may miss to add creep. That means you didn't really do long term. Then wrong stage duration. You did not consider the duration of the stage. Actual duration. STL applied too early. You have to apply the super dead load when it is really applied during construction. 6 months after the 2 months, 1 month, changes things. Results only saved at a final. You did not save the intermediate results. You missed the actual fun. Missing element activation. You did not add some group. You forget to add some group, important group in the analysis, and some part of the structure never got built into the analysis. It's quite possible. The structure wasn't complete. Foundation not modeled. So we just modeled fixed base. Like I said, soil structure interaction is a separate thing we will discuss, but that also affects this one because construction sequence with foundation settlement becomes more important than without that. Because now the construction, the settlement, and that are now combined together because of the interaction between soil and structure over time. Okay, summary and practice. So, single stage, not adequate, you require it. We miss the differential settlement. It's dangerous for transfer structures, outrigger. So this is just a summary, which whatever I just mentioned, we summarized that when we have to do that.